In the name of God, I'm Mohammad Ali Zarif, and today we're going to talk about our paper, which is about a chaotic multi-population ABC algorithm based on memory and levy flight for solving dynamic job shop scheduling problems. As you can see, the paper and our presentation is categorized to the following sections, which is introduction, related work, basic concepts, proposed method, experimental results, and finally conclusion and future works. As you may know, in the real world there are many practical optimization problems such as air traffic control, economics, nurse scheduling, and trade market prediction. Scheduling problems are one of the most challenging optimization problems. An environment is dynamic if it changes while an agent is in the process of responding to a perceived sequence. So, when a change occurs, the same problems which exist in static environments should be solved without any delay. There are two approaches to solve the mentioned problem. One of them is the traditional approach, and the other one is the dynamic approach. Traditional approach focuses on static, non-changing conditions, but many optimization problems in production systems, particularly job shop scheduling, are very complicated, and solving them by conventional optimization techniques is not possible. In the real environment of manufacturing, the sets of tasks which are needed to be scheduled change over time. This issue indicates the dynamics of scheduling problems. Dynamic approaches admit that both the problem and the solution may evolve in time. The easiest way to solve dynamic problems is to restart the search whenever a change is detected, but the information in previous resolutions would be lost. Reusing this information can also reduce the required time to find a new solution. A large number of researchers suggest PSO variants for dynamic optimization problems. Multi-swarm PSOs use a general technique which is inspired by multi-population evolutionary algorithms. In order to improve the diversity of the particles in DOPs, some of these methods are PSOLS, OLM-PSO, CC-PSO, and DOF-PSO. Multi-population BFO approach was proposed in order to adapt to dynamic environment. In this method, each population of the standard algorithm follows the basic rules with some modifications. Also, in order to take multiple optima simultaneously, a mechanism called interpopulation repulsion is introduced. And an example for multi-objective approach is multi-objective gray wolf optimizer for multi-objective flexible job shop scheduling. In the mentioned job shop scheduling problem, hierarchical job precedence constraints are also considered. In order to deal with FJSSP JPC, the objectives of make-span are simultaneously minimized, and the objectives are maximum and total machine workload. Dynamic job shop scheduling is an optimization problem which assumes that at the beginning of the schedule, n jobs are scheduled, and after that a set of n prime new jobs should be processed. All of the mentioned processes must take place on m machines. The next concept is multi-population ABC algorithm. Well, previous researchers show that multi-population methods perform well in dynamic environments, and they do better than other methods in many cases. Multi-population ABC algorithm splits the population into several subpopulations. By applying the mentioned method, the solutions will be spread over the search space. Therefore, high-quality solutions will be generated and the change in the problem will be tracked. The next concept is chaos theory. As you know, generating random numbers uniformly is very important for simulating complex phenomena. In optimizations based on random numbers, if chaotic values are used instead of random numbers, they are called chaotic optimizations. So far, many of these maps have been used to improve the performance of search and optimization algorithms. These maps have some advantages, which some of them are searching more precisely for global optimal calculation, avoiding getting trapped in local optima, and improvement in convergence speed. And finally, levy flight is a set of random processes in which the length of each walk follows the levy probability distribution function and has unbounded variance. Random numbers can be generated in two steps: generating steps which are based on levy distribution and choosing a random direction. Levy flight distribution is used in order to extract the information of search space. This can lead to increase of population diversity. In this paper, a multi-population chaotic algorithm with levy flight and memory to maintain proper solutions is presented. In this algorithm, we use chaos theory to create the initial population and variables that should be generated randomly. Therefore, in order to control the rate of convergence in the proposed algorithm, the initial population is generated based on chaos theory. The memory used in this method is a direct, explicit memory which is initialized according to chaos theory based on the logistic map function. Memory updates take place at random intervals. In this way, memory retrieval takes place when the environment changes. Recovering from memory is done by replacing the worst person of the main crowd with the best person in memory. The change in the environment is identified when the suitability of one of the individuals is in the population changes in the reevaluation process. Then the algorithm will identify the change and the memory retrieval process will be performed. Explicit memory exploited in order to gather useful information. It includes direct and associative memory. In direct memory, good solutions obtained by any person or the population are stored directly in the memory and used in the new environments. Since dynamic environment is cyclical, the use of memory increases the convergence rate of the algorithm. In order to omit the problems of ABC and based on the advantages of chaotic variable, chaotic multi-population ABC with levy flight algorithm which integrates multi-population ABC with chaotic variable and levy flight is proposed in our work. After the search process of each B, chaotic search is done in the neighborhood of the current best solution in order to pass one bare individual into degeneration. The steps of the proposed method are as follows. The first one is set parameters. The main parameters of multi-population ABC are initialized. There are 5 parameters in the algorithm, 4 of which are similar to basic ABC: number of B's, population size, maximum number of iterations, limit parameter, and another parameter is the subpopulation size, which shows the number of subpopulations. At first we assume that it is 2, and after that it can be either decreased or increased. The next one is initialize the population of solutions and memory. A set of solutions with a size of PS are generated based on levy flight distribution. The levy flight distribution is calculated, which is in the paper. And the next step is evaluate the population of solutions and memory. The fitness of every solution is calculated based on the objective function, which is problem dependent. The next one is divide the population. The population of solutions is split into m subpopulations. Each solution is appointed to a subpopulation. The subpopulations merge and redivide every time a change in the environment occurs. The decrease or increase of the number of subpopulations is based on the environment change strength. At first, the value of m is set to 2. The next step is assign chaotic ABC to each subpopulation. Each subpopulation has a CABC algorithm which has the following steps: setting CABC parameters, generating the population of solutions, assessing the population of solutions by using the objective function, updating the position by using employed B's, selecting the solutions by onlooker B's based on the value of their fitness function, and finally, scout B's generate a new solution by using the chaotic sequence. This step is run iteratively until a change in the environment is detected. The next step is check the changing strength. When a change is detected in the environment, two objective functions are calculated: the best solution before and after the environment change. If the subpopulation size is more than 2 and change strength is less than determined threshold, the number of subpopulations is decreased because the algorithm should be more exploitative. Otherwise, it is increased by 1. An individual that has the most efficiency is selected as the best individual in the population memory, and the least efficient individual is selected as the worst person in the main population. Then the best individual in the memory replaces the worst one in the population. And the final step is checking the stopping condition. The stopping condition is defined as the maximum number of fitness evaluations. If the stopping condition is met, the search process will end and it will return to the best solution. Otherwise, all subpopulations are merged and divided into m subpopulations, and the algorithm starts the first step again with a new generation. The moving peak benchmark is an ideal simulator for simulating dynamic environments. MPB involves n peaks in m-dimensional space with parameters that have real values. Altitude, width, and position of peaks can change over time. The values that have been used for MPB parameters are based on a paper which is referenced in our paper. Evaluation of the proposed method. There are several criteria for assessing the performance of evolutionary algorithms in dynamic environments. Most researchers have used offline error to evaluate the performance of their algorithms. So we have used this evaluation metric to compare the proposed ABC algorithm with state-of-the-art algorithms, which can be calculated as you can see on this slide. As you can see in the figure, our proposed method has better performance in terms of offline error than state-of-the-art methods. And finally, in this paper, a new algorithm based on multi-population ABC and explicit memory for optimizing solutions in dynamic environments is proposed. Also, in this algorithm, we use chaotic number generators instead of random ones, and we have introduced levy flight initialization. We use the proposed algorithm for dynamic job shadow scheduling problem, and according to the results, it is easy to conclude that the proposed method provides better solution than the other methods for the problem in terms of offline error and CPU time. The combination of the proposed method with other methods, including the hill climbing technique for local searches, can be a good option for future work. Furthermore, the proposed algorithm can be used to optimize real-world dynamic problems.